Hello and welcome. In the last few sessions, we were discussing the countability related results. And in the last session, we have seen that Cantor's diagonalization method can be used to prove that the set of all real numbers in the open interval 0, 1 is uncountable. One may now naturally suspect that if we list all the rational numbers in open interval 0, 1 in decimal form, and try to enumerate them and then try to apply Cantor's diagonalization method, we will probably be proving that the set of all rational numbers in open interval 0, 1 is uncountable. But if that happens, then the set of whole rational numbers will become uncountable, which is a contradiction to our previous argument and proof that the set of all rationals is countable. We are going to see that this is not actually going to happen, and we are going to see that Cantor's diagonalization method will fail to create or generate a rational number in 0, 1 because of the speciality of decimal representation of rationals. And for doing this, we will show that a rational number will be having a decimal representation in two special formats. One form is that either a rational number will terminate keeping only zeros in the decimal representation after a finite stage, or the rational will be having in the decimal form a block of digits repeating after a finite number of digits. We are going to discuss all these things in this session. The topic of our discussion today is decimal representation of rational numbers. Suppose that we consider a decimal number in the following form, 1.5325. Then of course we can convert this into a rational number by writing 1.5325 divided by 10,000 in fact. So by multiplying with powers of 10 on the numerator and the denominator, which is 1, so here we can take the denominator to be equal to 1. If we multiply with the power of 10 on numerator and denominator, we can easily convert this decimal representation number to a rational number. Therefore, whenever we have a decimal representation of some number which is terminating, in the sense that only finitely many digits are there after the decimal point, and after that, if at all some digits are there, they are all zero, because 1.5325 can be actually written as 3's after 0, 0, 0, etc. So only zeros are remaining after a finite number of positions after the decimal point. Then this is definitely going to be a rational number. So decimal representations that are terminating is always going to give rational numbers. That is observation number 1. So decimal representation of real numbers that are terminating in the above sense. After a finite stage, everything becomes 0 after a finite number of digits. Decimal representation of a real number that are terminating corresponds to a rational number. This is a very quick observation, because this can be proved also very quickly, because suppose that we have consider the number y.y1, y2, etc. up to some yn, and this is terminating, and after that just 0, 0, 0, etc. And then suppose we call this as equal to capital Y. Then there are n digits after the decimal point. Therefore we can multiply this with 10 to the power n. So 10 to the power in fact y equal to 10 to the power n y divided by 10 to the power n. Now this is equal to 10 to the power n y. If we are multiplying with 10 to the power n, then this becomes y, y1, y2, etc. yn, and after that this is an integer. Now this is going to be equal to 10 to the power n, and this belongs to q. Therefore, if we have a real number represented in the decimal form with only finitely many digits after the decimal point, and after those finitely many decimal after those finitely many digits after the decimal point, everything else is 0, and then that particular decimal representation corresponds to a rational number, and we can find that rational number in this way. Okay, this is one possibility. And now the second possibility is that if the decimal representation is not terminating but a fixed block of digits are repeating infinitely, then that representation also corresponds to a rational number. We have seen that in the case of 0.4999 etc., we tried to convert that into a rational number, and we have in that proof we have seen that that actually corresponds to 5 by 10, and the same technique we can apply here. So the second observation is the following: decimal representation of real numbers that are not terminating but a fixed block of digits is repeating corresponds to a rational number. So for that, let us consider a representation in this following form: y equal to y point y1 y2 etc. Suppose up to yk, these digits are randomly appearing, and after that yk plus 1 etc. up to some yn, and suppose that these digits are repeating infinitely many times, like again yk plus 1 etc. yn. This block of digits are repeating infinitely many times, yn, and so on. And in this case we will usually use the notation y point y1 y2 etc. yk to denote that these digits are the infinitely repeating block. We will put a line over these and this simply means that y point y1 y2 etc. up to yk, they are some random digits, and yk plus 1 up to yn is repeating infinitely many times as a block. This is a non-terminating representation of a decimal representation in which a block of digits are repeating infinitely many times. So now we can show that this number y, this number capital Y corresponds to this decimal representation capital Y corresponds to a rational number in the following way. So we have actually done this in the case of 0.499 etc. The same technique we are going to use here. So we need to bring this y1 y2 etc. up to yk just to the left of the decimal point. For that we are going to multiply y with 10 to the power k. So 10 to the power k y is equal to y1 etc. yk. Now only the repeating block of digits are remaining on the right side. This is repeating infinitely many times. This is 1. Now we are going to bring, as in the previous case, this yk plus 1 etc. yn also one block to the left of the decimal point. For that we need to multiply with our 10 to the power n minus k. So 10 to the power n minus k, 10 to the power k is going to be equal to y1 etc. yk. Now yk plus 1 etc. yn, and after that once again yk plus 1, because this is infinitely repeating this block, so yk plus 2 etc. yn, and this is again repeating. Now if we subtract from the second expression from this second one, if we subtract the first one, you will get this is 10 to the power n, this is 10 to the power k. So 10 to the power, this is 10 to the power n minus 10 to the power k of y is nothing but, so the digits after the decimal place are same in both these expressions, therefore those will get completely removed. So what is remaining? y, this is larger, y1 etc. yn minus y1 etc. yk. Remember that this is an integer, this is also an integer, so the difference is an integer. So capital Y therefore becomes y equal to, so these two expression, the difference of these two, we're just copying. So the difference of these two we have to keep here, and that divided by 10 to the power n minus 10 to the power k. So this representation is on the top we have a natural number, on the bottom we have a natural number, therefore this corresponds, this is a rational number. Therefore if we have a decimal representation in this way, that means after the decimal point, after some finite digits, a block of digits are repeating, then that decimal representation corresponds to a rational number. So we have now seen two forms in which rational numbers are represented in the decimal form, one in terminating form and the other in non-terminating form, but block of digits are repeating. Our claim is that these are the only two ways in which a rational number can be represented in the decimal form. So this is the claim. R belongs to Q can be represented only in one of the two forms given above. This is the claim finally we have. So if we have a rational number, if we want to represent it as in the decimal form, then we can have a decimal form only in one of the above forms. That means either it's a terminating decimal or it's going to be a non-terminating decimal, but block of digits are repeating infinitely many times. To get an idea about how to establish our claim, we should probably try to understand how do we convert a rational number into the corresponding decimal form. For example, we will consider the numbers 29 and 29 by 4. Suppose that we are looking at 29 by 4. How do we convert this into decimal form? So initially we try to divide 29 with 4, and we see that we can 4 is contained 7 times, so we write it as 28. Now what is remaining? What is the remainder? Remainder is 1. So 1 is not divisible by 4, therefore we multiply this 1 with 10, so 10, so that that number will be above 4. So we are now considering 10, so to balance we will divide with 10, therefore we have a decimal point here. So this is nothing, this is not 1 now, this is actually 10. We are trying to divide 10 with 4, therefore we know that it's going to be 2, because 10 with 4, that's 8. So this is now 10, and therefore we write it as 8. Now 2 is remaining. Now 2 is not divisible by 4, therefore we will again multiply with 10. So now it's 20, and so 20, and we know that in 20 there are 5, therefore here we have 20, and that's it. So we are getting 7.25. See that we are trying to divide the remainder again with 4 by multiplying it with a suitable power of 10. Then we are subtracting whatever multiples of whatever is the largest multiple of 4 contained in that 10 multiple, and we are writing the quotient here. So the quotients here we are writing on the top, and the remainders we are multiplying with 10. That is what we are exactly doing to convert a rational number to decimal form. We are going to basically this quotient and remainder comes from the division theorem. So we have to make use of division theorem, and okay, we will see an example first. This example using division theorem we will see first. So initially we will write 29 by 4. We want to bring to decimal form. This is our aim. We will say that first, how to do it. So 29 we will write as 4 into 7 plus remainder 1. Now the 7 we are taking, 7 is very important for us. Now what is remainder? Remainder is now 10. Remainder is 1. 1 cannot be division. 1 is not divisible by 4. So we take 10 to the power 1 into 1. So this is going to be equal to 4 into 2 plus 2. So the remainder is now 2. Now 2 is not divisible. See, since we multiply it with 1 power of 10, we will write 7 just decimal point. If we multiply with 10 square, we would have written 7.0 here. So now 4 into 2 plus 2. Now we are continuing the division theorem. This is division theorem applied. Here we are using division theorem. So now we have 2 is not divisible by 10 but by 4, but now we can multiply with 1 power of 10. That's enough. Therefore this is equal to this is 20. Therefore 4 into 5 plus now the remainder is 0, and therefore no more further divisioning actually required here. So this quotient is 5. Before that 7 here multiplied with 10, therefore after decimal point 2. Now multiplied with another 10, therefore it is 5. This is what we do for converting 29 by 4 rational form to decimal form. Exactly the same procedure we are going to apply in the general case also. Now we go to the general case where we are trying to see what happens when we try to take decimal form of m by n. So consider m by n in Q with m and n natural numbers. Of course, when we can consider negative rations also, there is no difference in the proof, so we stick to the positive case. So by division theorem, we can write m equal to n q1 plus r1, where 0 less than or equal to r1 less than n. Now we don't know whether this r1 is 0 or not. If r1 is 0, this is a perfect division, and therefore the process is terminated. There is no more division required. And so in that case we have m by n, in which case if r1 equal to 0, then m by n is going to be just equal to q1. So we are done. Therefore this is a terminating decimal representation, q1.0. Now if r1 is not equal to 0, we need to continue the division. If r1 not equal to 0, we know that r1 is less than n, and therefore we cannot divide r1 with n. So we need to multiply r1 with some power of 10 in such a way that 10 to the power k1 into r1 will be greater than or equal to n. So let k1 belongs to n be the least, such that 10 to the power k1 r1 is greater than or equal to n. So we multiply r1 with this and write n q2 plus r2, where 0 less than or equal to r2 less than n. Therefore we are continuing our decimal representation in the following way. So the first digit is going to be equal to q1. The second digit, suppose that we are multiplying with 10, then we need not put any 0 here. Suppose that we are multiplying with 10 square, then we need to put a 0 here, and after that the quotient q2. So here we have how many zeros are required. So we require, so k1 minus 1 zeros, and then after that we have q2 here. Now if r2 is equal to 0, this process is terminated. If r2 is equal to 0, then the process terminates here. No more further divisioning required, because we have the decimal representation q1.000 etc, k1 minus 1 zeros, and then q2. If r2 is not equal to 0, then we need to continue this process. If r2 is equal to 0, we stop here. If r2 not equal to 0, let k2 belongs to natural numbers be the least, such that 10 raised to k2 r2 equal to n q3 plus r3, where again 0 less than or equal to r3 less than n. Now we have q3 here, and therefore the decimal representation will be q1 point some zeros here. Here how many zeros are there? There are k1 minus 1 zeros. After that we have q2, and after that we have again k2 minus 1 zeros, and after that here we have q3. And suppose r3 is not 0. If r3 is not 0, we will continue. If r3 not equal to 0, we continue, and so on. If at some rm it becomes 0, if at some if we get some rn to be equal to 0, if rn is equal to 0, then the process terminates there. And the decimal representation is with decimal representation the following way. What is the decimal representation? q1 point, we have here k1 minus 1 zeros, after that q2, then we have k2 minus 1 zeros, etc. It is terminating at rn, therefore till rn minus 1 we have to go. Corresponding to r2 we have q3 here, so corresponding to rn we have rn is 0, therefore we don't require that further coefficient, so up to q n we have to go, etc. like this. And finally we have qn here. How many zeros are here? Kn minus 1 zeros. This is the decimal representation. This is terminating. Now suppose that for no n this r is 0. On the other hand, suppose the remainder never becomes zero. Suppose that the remainder never becomes 0, and in that case we have remainders in the following way: r1, r2, etc. Going on like that. Now how many remainders are there? Possibly there can be at most n distinct remainders, because all these remainders are obtained by dividing the number with n, therefore at most n distinct remainders are possible there. So if this the sequence is going on indefinitely, therefore some of the remainders must be definitely repeating. So some remainders are repeating. Suppose that r1, r2, etc. up to rm are all distinct, and rm plus 1 is one of the previous remainders. See, some remainders are repeating, because we know that by pigeonhole principle, if there are n holes and there are more than n pigeons, then definitely at least 2 of the pigeons must share the same hole. The pigeonhole principle we are using here. If we have more than n remainders, infinitely many remainders are here, the process is never terminating. If you have more than n remainders, and suppose that all the remainders are cannot be therefore distinct, because at most n remainders are there, therefore after the nth remainder, what the remainder must be, one of the remainder must be the previous one. So suppose that r1, r2, etc. up to rm are all distinct. Suppose m is a natural number such that r1, r2, etc. rm are all distinct, and rm plus 1 is one of the previous remainders. So Rn plus n is the one of the previous remainders, means that Rn plus 1 belongs to R1, R2, etc. Rm. That is Rm plus 1 belongs to R1, etc. R. Yeah, this is what's meant by saying that this is one of the previous remainders. And suppose that this m plus 1 is, suppose this m plus 1 is equal to Ri. So to divide R plus 1, we have to divide Rm plus 1 with n. Therefore we have to multiply Rm plus 1 with some k, but for dividing Ri, we multiply Ri with nothing but 10 to the power, what is it exactly? We divided Ri with 10 to the power ki. So therefore 10 to the power ki Rm plus 1 equal to 10 to the power ki Ri, and we get this to be equal to n times qi plus 1 plus, but if we divide Ri 10 to the power ki Ri with n, we will be getting the remainder as Ri plus 1. Therefore after Rm plus 1, the next remainder is Rm plus 1 gives rise to Rm plus 1 is nothing but this is equal to Rm plus 1 is nothing but this is equal to Ri. Next remainder will be Ri plus 1. If next remainder is Ri plus 1, next is Ri plus 2, etc. Going on like that, we will get the remainder Rm, and after that it will be again Rm plus 1, but that is nothing but Ri. So the remainder is Ri plus 1, etc. Rm will be repeating indefinitely. So the remainders will be, what are the remainders? R1, R2, etc. Rm. After that we have Rm. After that Ri. If Ri is there, Ri plus 1 is the next remainder. After that again Rm. Next again it's going to be Rm plus 1, which is Ri plus 1, which is Ri, which is therefore next one will be Ri plus 1, and etc. Then we have Rm. Therefore these remainders are going to repeat infinitely, and therefore corresponding quotients. So corresponding quotients, what about the quotients? Therefore we will get q1, q2, etc. qm, and after that corresponding to Ri we are going to get only qi plus 1, etc. qm. Now again this corresponding to R1, what is the, when we are dividing with R1, R1 produces the quotient Q2. So we should write here quotients are not corresponding to, this is going to be Q2, Q3, etc. Qm plus 1 are corresponding to Ri. We have the quotient Qi plus 1, then Qi plus 2, etc. Qm plus 1, etc. The quotients also will be repeating. Therefore what will be finally the decimal representation? The decimal representation will be m by n will be equal to q1 point, we don't know how many zeros are here, q2 k1 minus 1 zeros will be here. After that q3, here we have k2 minus 1 zeros, etc. After that we have qm plus 1. After that it's going to be after qm plus 1 it's going to be again qi, and this is going to be again ki minus 1. This is qi plus 1, etc. qm plus 1, etc. Therefore we can write it to be q1 dot q2, zeros are here infinity in between, etc. qm plus 1, and after that qi plus 1, etc. q m plus 1, this is repeating infinitely. So this is the final decimal representation, and this is a representation which has non-terminating but infinitely repeating blocks decimal representation of the rational number. So we have proved that if the decimal representation is not going to terminate, then the decimal will be, a block of digits will be repeating infinitely many times. So we will see a few two examples also in which gives which explains what we have exactly done in the previous abstract exercise. So following is an example demonstrating what we have done in the previous exercise. So find the rational form of find the decimal form of 1091 by 990. Find the decimal form. So 1091 by 990 is the question. So we can write 1091 equal to 990 into 1 plus what is the remainder? It is 101. So we are starting our decimal representation with 1 here. So 1 point. This is our Q1. This is our R1. So R1, if we multiply with 10, then this will be 10 to the power 1 into 101. That's equal to 1010. This is equal to 990 into again 1 plus what is the remainder? Remainder is 20. So the quotient, this is Q2, this is R2, remainder is not 0 still. So we are continuing the decimal representation. So this is going to be equal to 1.1. Therefore, now the remainder is 20. So 20 equal to, so if you multiply 20 with 10, that is not going to be a multiple of 990. So we need to multiply with a higher power. So 10 to the power 2, if you multiply, that's 100. So it is 2000. So we need to multiply with 10 square. So we will put a 0 here. This is equal to 2000, and that is 990 into 2 plus 20 again. So this is 990 into 2, therefore 1080 plus 20. This is our Q3, this is our R3. So Q3 we will write here, but since we have already taken 10 square, therefore we already have here 1 0 included. So 2 is the quotient Q3. So this is Q1, this is Q2, this is Q3, and this is K1 minus 1. K1 is 2, therefore K1 minus 1 is 1. So 1 0 included here. This is 1 0. Now we can again continue this, but now observe that what are the remainders that we are getting here. First remainder is 101. Remainders so far we have seen 101. Now it is 20. Now it's 20. So these remainders are repeating. So what will be next after that? So 20 is equal to this 20. This is remainder 1. This is remainder 2. This is remainder 3. But R3 is equal to R2. So again the remainder will be if you divide with R2. If you are dividing R2 with this n, we have to take a square, and then we will be again getting R3 equal to R2 itself. Therefore we will be again getting a 0 here. We will be again getting 2. We will be again getting 0, again 2, etc. Go on like this. So this is going to be Q3. This is going to be again Q3, etc. So we have only 2 distinct remainders. One is 101 itself, and the next one is 20. Therefore the decimal representation is, so we are terminating, we are stopping here. Therefore decimal representation finally becomes 1.102, 1.102, 02, 02, etc., which is equal to 1. We use the following notation: 0, 2 as the repeating block. So this is what we did in the previous exercise. So every rational number in the decimal form can be either represented as a terminating decimal, or it can be represented, or the other way in which it may probably appear is non-terminating but block of digits repeating. These are the only ways in which a rational number can be represented in the decimal form. We started the session with another question that can we use Cantor diagonalization method to prove that the set of all rational numbers in the interval open interval 0, 1 is uncountable. So the question is this. Question now is this: can Cantor's diagonalization prove that the set of all rationals in 0, 1 subset of R is uncountable? Or Q intersection open interval 0, 1 is uncountable. Okay, and the answer is actually no, because of the special nature of decimal representation that every rational number possesses. Because see that suppose that we are listing rational numbers in the following way. Suppose we list rationals in 0, 1 like f of 1 as 0.a11, a12, a13, etc. f of 2 as 0.a21, a22, a23, etc. f of 3 as 0.a31, a32, a33, etc. And suppose that we use the Cantor diagonalization method to produce something that is not in this f of 1, f of 2, etc. Suppose that y equal to 0.y1, y2, etc., y3, etc. is constructed in such a way that yi is not equal to aii, then we will be definitely getting an element, then y will not be in f of 1, f of 2, etc. That is for sure, because Cantor diagonalization is not going to actually fail. It will definitely produce a y which is not in f of 1, f of 2, f of 3, etc. But the important thing is it is not enough to get just a number that is not in this list. So what we are saying here is definitely y is not in f of 1, f of 2, etc. But see that to say that y is not in this list and therefore the set of all rationals in 0, 1 is uncountable, we must actually produce a number y that is in 0, 1 that is a rational also. But y needs to be a rational to say that our listing or our enumeration is not complete. But for y to be a rational number, it is necessary that y must be in one of the previous forms, but the candidate's diagonalization produces just some number, and there is no guarantee that y will be a rational number. For y to be a rational number, the rational representation must satisfy one of the two conditions that we have seen above. But Cantor's diagonalization does not guarantee any such form for y. So Cantor diagonalization does not guarantee that y is a number which is terminating or has repeating block of digits. Therefore, Cantor diagonalization cannot prove that Q intersection 0, 1 is uncountable. We cannot use Cantor diagonalization to prove the uncountability of Q intersection open interval 0, 1, which is not, of course, true also. So we have answered here that why Cantor's diagonalization cannot be applied to prove that the set of all rationals in the open interval 0, 1 is uncountable. Cantor diagonalization produces some decimal number, but not all decimal numbers are rational numbers. The decimal number will be a rational number if and only if it is either terminating or it is not terminating with the block of digits repeating infinitely. But Cantor diagonalization does not give any guarantee to us saying that the number it produces is going to be in one of these forms, and therefore we are not definitely finding a rational number. We cannot confirm that the diagonalization gives a rational number in the open interval 0, 1. And by this we are completing the problems related to Cantor diagonalization and uncountability, and we are moving to our next topic, in which we are trying to see that how can we, if at all we can, how can we categorize sets based on the number of elements in sets. And that is going to be the final topic in our the sequence of talks related to countability. Thank you.